Hello everyone and welcome to another episode of Investigation. In today's episode of Investigation, I will go over e to the x derivative. And there's no daily problem today because what we learned previously are not that hard. Trigonometric differentiation, they can be just derived from sine and cosine. As long as you get that sine and cosine, you will be good to go. And today we will go over a rather new type of function that we are going to able to differentiate after this lesson. So that is exponential functions. Before we try to take the derivative with respect of x of e to the x, we need some background information on how to represent e. There are two ways to represent e. One of the way is that e is equal to the limit as n approaches infinity of 1 plus 1 over n to the n. Or it can also be represented as the limit of n approaches infinity of 1 plus n to the 1 over n power. And with that, we can calculate the derivative of e to the x. But before that, if you wonder how these two formulas are gotten, I will link a card over here so that you can check it out. And his videos are pretty nice. So over here we have the derivative with respect of x of e to the x. And that is equal to the limit as h approaches 0. Of course, we're using the definition of derivative again, because we're actually differentiating a new type of function, and we really haven't done these types of exponential functions before. And we can get this e to the x out, something like that, and that is e to the h minus 1 over h. And obviously e to the x doesn't include h at all, so we can just get that out of the limit. So that's e to the x times the limit as h approaches 0 of e to the h minus 1 over h. Now we're a bit stuck, but we can use a smart substitution over here. So we can substitute n, let n be e to the h minus 1. Then we can have n plus 1 is equal to e to the h. How do we get h? Because we will need that h to substitute as well, then we can take the logarithm of that. That will be h is equal to ln of n plus 1. If you wonder what ln is, it's just log with base of e. So that's cleared out. And we can rewrite this expression as e to the x times the limit as h approaches 0 of n over ln of n plus 1. That's what we use this and this to substitute. And when we have that, we can simplify it even more. So that as h approaches 0 over here, we can actually find out that this h over here, if this approaches 0, then that will be e to the 0 minus 1. If h approaches 0, then that will be 1 minus 1, which is 0. So as h approaches 0, n also approaches 0. So we can completely substitute it as e to the x times the limit of as n approaching 0 of this stuff. And let's proceed. So that would be equal to, what we have is we can multiply 1 over n on both top and bottom of the expression so that we can get, this is the limit as n approaches 0, the top n times 1 over n, that's just equal to 1, And the bottom would be equal to 1 over n times ln of n plus 1. And after having that, we can try to simplify it even more using the function of learn again. So what we have over here is we actually decompose it like that. So we can use the property of logarithm to put this inside as an exponent. So that will be the limit as n approaches 0 of 1 over this learn, this thing. So that's n plus 1 to the 1 over n power. And the only thing that involves n over here is this blue expression over here. Then the other things we can just get out, and it doesn't require the limit anymore. So that will be e to the x times 1 over learn of the limit as n approaches 0 of n plus 1 to the 1 over n power. We can put that n inside the parentheses. And we know that this is exactly one of the representations of e over here. Actually, I wrote that wrong. This should actually be as n approaches 0. My bad. And that is exactly our definition of e. It's not really a definition of e, but it's an expression of e that we can use. That will be e to the x times 1 over learn e. And we know that learn e, which is basically log base of e, and that is simply equal to 1. And that will be e to the x times 1 over 1, which is e to the x. And let's recall what we tried to differentiate. What we tried to differentiate is actually e to the x. So what we get is e to the x back. And if you look at the graph, it's actually exactly correct. If you look at the graph of e to the x, something like this, then the slope at this x is just e to the x. This is one of the fascinating things in calculus, that you really find it very clean and neat after you do a lot of math. And that is also why I enjoy math so much. Thank you for watching this episode of Investigation, and I will see you in the next one. Goodbye.